Shall we start?
I am ready.
Yeah. Good afternoon. Okay. Good afternoon, all. Thank you for registering for this webinar. I'm Rakhi Pote. Welcome you all for the webinar Isometric Inequality by Dr. Alexandra Giron. Today's speaker is Dr. Alexandra Giron, Associate Professor in the Department of Mathematics and Statistics, Laval University, Canada. I welcome you, sir, for this webinar, and thank you for accepting our invitation and giving your precious time for us. Okay, and his areas of interest is spectral geometry, isoperimetric problems, and geometric analysis. He has completed his BSc in Mathematics, University of Montreal, MSc in Mathematics, University of Montreal, PhD in Mathematics, University of Montreal, and he did postdoc from University of British Columbia. He has presented many papers in spectral geometry, and not the least, but citation is 587. That's like something big. And welcome you, sir, for this webinar. Over to you.
Thank you. So, thank you very much for this nice presentation. I would like to extend my most sincere thank to Dr. RaGa Hampioli, Head of Department, Dr. Jayan Kitur, Principal, KLS Gokte Institute, and also, of course, to Rakhi Potter for giving me the opportunity to present my work here and for meeting you in such a incredibly far distance geographically this morning. I mean, for me, it is this morning. It is 5:30 in the morning here. Before I start with the mathematics, let me just maybe tell you my path through to which brought me here. So I did undergrad in mathematics in Montreal, and I was very fortunate to have very good professors who thought I should do a master's degree and then a PhD degree. And as you probably know, when we do a career as a research mathematician, we travel a lot to go to conferences and so on, or at least it used to be that before this pandemic came. And luckily now we have a virtual world to travel. A few years ago, I was at a school in Beirut in Lebanon, and this is where I had the opportunity and chance to meet Miss Rakhi Potter. And so we kept in contact, and that is how it is possible for me to be here now. So I don't know all of your background in mathematics, so I prepared a talk about the isoperimetric inequalities, which will start with very easy subject and move on to more and more abstract mathematics. So it is quite possible that in the beginning, some of you will find what I'm doing trivial. And it is also quite possible that at some point, some of you will find it very hard to follow later on. So there will be a material at many different levels. My goal is to illustrate this nice topic, which is, well, maybe you notice now that the slide is not in English. It is because in that part of Canada where I live, the main language is French, actually. It's called Quebec. So I live in the city called Quebec City. And the main language here is French. It's a small part of Canada where French is the main language. Of course, I will move on to English. So what is the topic of the talk? So if you look at this picture, it is a village somewhere in Africa, and you notice one peculiar thing is that it seems to be round. So it is enclosed by a round fence. And if you look at some animals that are protecting the offsprings, they will often form a round shape around them to protect them. And if you look at some cities, especially older cities, you will notice that they are enclosed in with walls that are usually round. They're not like rectangular and thin, long walls. They are usually round. So why is that, you may ask? And one of the reasons that we will discover is that if you have a certain area, a certain land that you want to build and protect, it is easier to do so if the boundary that you are surrounding is the shortest possible, because you will need a shorter fence or less army people to protect it or something like this. Also in nature, there are many different places where the round form and spheres and so on are represented. Of course, you can see the planets and the stars. But if you look at a soap bubble, it is a very good example of something that is very near us and is circular. And why is it circular? Well, it is in a sense because the bubble itself, the boundary of the bubble, it has a prescribed area. Once it exists, it has this amount of soap. You cannot add or remove soap. And so nature wants to make the volume inside this as large as possible. Or another way to say it is that you have enclosed a certain volume, and then when you enclose this volume, the shape can move around, and it will be beneficial for energy consideration to have the smallest possible surface around this volume. So nature will choose a round shape for this. Can you just tell me if you hear me properly? Can everyone hear me properly? Can someone just confirm this?
Yes, we can hear you.
Okay, thank you very much. Okay, so here is the plan of my talk. I will first talk of the historical origin of isoperimetry. I wrote mythical rather than mythical because it is not completely clear if what I'm going to say there is part of history or of some made-up history of myths. Then I will speak of easy examples of isoperimetry, not for all possible shapes, but just for rectangles, then for triangles. Then we will speak about general polygons. And then we will try to describe how a complete proof of this has been given. So my goal here is to maybe find a way to show that it is very important to be rigorous when we do mathematics. We are very good at computing things, but maybe keep in mind that in all of what I will say in the first part, there is a big mistake everywhere. But it is not an easy mistake. It's not a computational mistake. It is a mistake in the foundation, in the very idea of what we are doing. And this mistake is so difficult to spot that the mathematicians who did this did not see it themselves. It took several hundred years for them to see it. So okay, I say it's a mythical origin. This is a very Western story. It is in the Greek tradition. So there was a princess sometime before the current era, so before Jesus Christ. Her name was Elisha, or she's also known as Dido. So Dido is maybe the most common name. And she was a Phoenician princess. She was the daughter of a king called Tyr. And her brother assassinated the husband of the princess because he wanted to become the king. So the princess Elisha, she escaped with her entourage. They flew across the Mediterranean, not they flew, but they sailed across the Mediterranean Sea, and they ended up somewhere on the coast of North Africa. And there she met some local king, Yerbas was his name. And she made a deal with the king. And the deal was that he allowed her to get land. She could create a city or maybe just a plot of land near the sea on the coast that would be as large as she could enclose using the hide of an ox. And so she was very clever, and she cut the hide of the ox into a very thin rope. And then once she has the rope, you can see here the part below is mer, it means sea in French, so here I did not translate this. And the part above is the terre, which means the land above. So you can imagine that the part in red is the rope that she has. And what does she do to enclose? The rope has some length. It's a fixed length. You cannot make the rope longer. She built it with the ox hide. She could do this, or maybe she could do this, but that's not very clever because the area that is enclosed by it is not very big. So to get the biggest area possible, the best idea is to use a half circle, and it is written in some classical Greek text that she had the right idea and made a half circle. And this is the legend of the foundation of the city of Carthage. This is where now Tunis is, in Tunisia. And so the problem that she solved is illustrated here on this wood carving. The problem that she solved is known in mathematics as Didot's problem. So the question that is asked by this problem is to look at all curves that have length p. So we look, say, at all. I wrote perimeter p.
Master, please.
Yes.
Switch off your camera.
You want me to switch off the camera?
Sorry.
Okay.
You continue.
Okay, sorry. Okay.
No,
Okay, I thought someone was asking me something.
that's fine.
Okay, so the length of the curve is p. So you imagine you have a fixed length of curve. And then you want to find the figure that has the largest area. Okay? And I just told you the solution. If you look here, you have a half circle. And the half circle will give the solution to this problem. The largest green area here will be obtained when I take a half circle. Now, this is the Didot's problem. The problem I want to speak about is something very similar that is called the isoperimetric problem. Instead of looking at a curve that is bounded by a line, like in this case, I want to look at a closed curve. And so Didot's problem was a very good model for a situation where you have sea and land, because you would enclose something that touches the sea. But if you want to enclose rather a closed area of land, then you imagine that you have some length of rope, and you want to make a shape with it that will have the largest area. Or you can also ask the question in reverse. You look at all planar plane figures that have a specified area. You decide of the area, and you want to see which one will have the smallest perimeter. And both problems are equivalent, and the solution is to take your rope and make a circle with it. That is the solution. Now, I told you the solution of the problem that I am considering in this talk, and it is known for several thousand years. So why am I speaking about this? One could argue that since it is known, I have ended my talk and there is nothing to say about it. The problem is that is the following. People knew the solution to this, but nobody knew how to prove that is the right solution until quite late in the history of mathematics. So for all the prehistory of mathematics, even, and then in the Middle Ages and so on, everybody knew that the solution should be a disk. If you want largest area, you use a disk, but nobody could give a convincing proof. And the goal of my talk is to take you through several attempts at proving this, all the way to maybe showing one of the earliest complete proof of this at the end of the talk. So let me ask a simpler question. Instead of looking at all shapes, all possible figures, let's look just at rectangles. So rectangles are more simple than any than all of shapes, because you have just two parameters, one side length and another side length. So if I ask the question for rectangles, again, as before, the formulation 1, if I look at all rectangles that have a specified perimeter, I'm asking which one has the largest area. Or I could ask, if I look at all rectangles that have a given area, which one has the smallest perimeter? Okay, and let's solve this problem. This is something you have probably done several times in some exercises. So you imagine that you have all rectangles that have perimeter P. So for instance, here I have a picture of a rectangle, and I imagine that the side lengths are x and y. If the side lengths are x and y, it means the area is x times y, and the perimeter is twice x plus twice y, because there are two sides of each. Now, if I consider P to be the fixed perimeter, it's a constraint. I propose that this is the perimeter, and so I can solve for y in the equation for P. And so y, if I divide by 2 and subtract x, I can say that y is the perimeter divided by 2 minus the other side length. And so if I substitute y, that is given by P over 2 minus x, into the formula for the area, I get a formula for the area that depends only on the side length x, because P is a fixed perimeter. So I guess that the area is minus x squared plus px over 2. And now if I want to find which rectangle has the largest area for this given perimeter, I just need to find the maximal value for this formula with x. So if I look at this formula, a of x will give me minus x squared plus px over 2. And I say, so if you look at this formula as a formula for x, it is a parabola that is turned downward. Right? Its concavity is down. And so I just need to find the value of x where the maximum is reached. And to do that, there are several ways. It's just a quadratic function, so I could use formulas for quadratic functions, or I could just find where the derivative of this function is 0. If I look at the function minus x squared plus px over 2 and I differentiate it, I will have minus 2x plus p over 2. And this is equal 0 exactly when x equal p over 4. And now if I substitute x equal p over 4 in the formula for y that I have given here, I said that y is p over 2 minus x, then I get that y is p over 2 minus x, that is for this specific value of x, it gives p over 2 minus p over 4, and it gives p over 4, which tells me that for this formula to reach its maximum, I must have that x equal y, and x and y are the side lengths, so I have a square, and the side of the square are exactly p over 4. So I have maximized the area under the constraint of a fixed perimeter, and I find that the solution is a square. It's very satisfactory. It's not as hard as finding among all shapes, but for rectangles, we know the best one is the square. Okay? Now I will move on to triangles. Triangles are more difficult to do. But Euclid proved that among all triangles with the same area, the equilateral triangle has the shortest perimeter. Now I wanted to show you something for this. I wanted to display a program for this, but my computer is freezing each time I try to do this. So if I draw something on a sheet of paper, I hope you can see this. I hope it works. Raki will tell me if this works. I have drawn two parallel lines. Raki, do you see this?
Hello? Yes, sir?
Yes, sir.
Okay. And if
I cannot see. What you are writing?
I want to do two parallel lines.
Okay.
Okay. Maybe I will just describe in words. Imagine a triangle in your head. Okay. If you have a triangle and its base, you fix the base for the triangle, and the height of the triangle is fixed. It's h. But the point that is above the height, it can move parallel to the base. Okay, so you have the base of the triangle, and then you have a point that is somewhere on a parallel line at height h above, and you can move this one. So you have a family of triangle. They all have the same base, but the apex can move on a parallel line. So all of these triangles, they have the same area, because the formula for the area of a triangle is the base times the 8 divided by 2. So the base is fixed. I do it physically like this, and then I move the apex somewhere like this. And what I want to say is, when I do this, all these triangles have the same area, but if I put the apex in the middle, then the perimeter will be smallest, because the two sides that are free to move, well, if I go very far to the left or to the right, then they will have perimeter going to infinity, and when I move to the middle, they will have the smallest perimeter, and when I move to the sun, they will have the largest perimeter. So if I take any triangle, I start with any triangle, I can consider one of its sides as the base, and move the other, the corner that is opposite to it, parallel to this side. And I say, oh, if I choose this in such a way that the two sides are of the same length, then I will have decreased the perimeter. So if I do this with each side, I can keep the same area but lower the perimeter. And in the end, if I do it with each side, I will have obtained equilateral triangle. So for now, we just take this for granted, and I don't know how it will be for you. Maybe you have to write a report on this talk or something. You can maybe try to think about what I'm saying now and write something about this. Okay? In any case, the point is, for triangles, there is a geometric proof that is like this. Okay, now the general case is much more complicated. Now I have spoken about rectangles and triangles. Rectangles, the best rectangle is a square. It is a square is a regular polygon with four sides. And for triangle, it is the equilateral triangle that is the best shape because it has the largest area or smallest perimeter. And it is also the regular polygon with three sides. So you guess with me that the best shape for a polygon with n side would also be the regular polygon. But to state this in a more precise way, let me give a different formulation of the general result. The general result is for any shape, not just a polygon, even one with a curved boundary. If I look at the area and perimeter, then the best shape for fixed perimeter will be to have a disk, so a round shape. This will have the largest area. And the best shape for, if I fix the area to have the smallest perimeter, I need the disk also. And one way to state this in a more precise mathematical way is through what we call the isoperimetric inequality. And the isoperimetric inequality is what is written here. If omega is a plane figure, so any plane figure that is with bounded area and with some perimeter, then we have the following inequality. 4 pi times a is smaller, a is the area, is smaller or equal than pi square, p square. Okay, and with equality if and only if omega is a disk. So imagine if you take omega, a disk of radius r, this means the area is pi r squared and the perimeter is 2 pi r. If you plug a equals pi r squared in this inequality and p equal 2 pi r, you would get equality because they give the same thing on each side. So this is an equivalent formulation of the statement. In this statement here, if I divide on each side by p squared, it tells me that the ratio 4 pi times the area of a planar figure divided by its perimeter square is smaller or equal to 1. So in order to prove that the best shape is the disk, one has to say that for the best shape, if I take the best shape, it will have 4 pi a divided by p squared smaller or equal to 1. Okay, and I call this quantity 4 pi a divided by p squared, so 4 pi times the area divided by perimeter squared. I call this the isoperimetric ratio of the figure. And our goal is to show that this is smaller or equal to 1. Okay, but historically it was not presented like this, but now my goal is to show you a sort of a long road, historical road, to proof of this. And the first attempt at such a proof were given by Zenodorus. Zenodorus lived somewhere a few hundred years before the current era, so a bit more than 2,000 years before. He was a Greek mathematician in the classical period. In fact, the work of Zenodorus was lost, but the way that we know about it is because in the writing of other people, like Theon and Pappus of Alexandria, they write about this, and we know it existed, but it's been lost. And his claim Okay, here in this claim, I speak about n-gons. What I call an n-gon is a polygon with n side. So, for example, a 3-gon is a triangle, a 4-gon is a rectangle, and so on. So, a 5-gon is a pentagon. So, if I fix n, and I look at all the n-gons that have a given area, all the n-gons that have a area equal to 1, for instance, then I'm asking the question, which one has the smallest perimeter? And the solution is that it is the regular n-gon. Now, what does regular n-gon means? Regular means that they have all the same length of the sides and also all the same angles. So, for example, a square is a regular 4-gon because the 4 sides have the same length, and also the 4 angles are right angled. Okay, so the solution, the question, the theorem of Zionodorus says, if I look at all, for instance, pentagon, the one that has the smallest perimeter among those with the same area is the regular pentagon. Or again, I could have stated it reversed. If I look at all the pentagon with the same perimeter, I could say that the one that with the largest area is the regular pentagon. You can always state it in 2 ways. And the way I want to give you an idea of the proof of this. It will be a little bit difficult because I cannot show you my animation that I made. I'm sorry about this. So I'm stating it again here, the statement, and the proof goes as follows. The first thing is, imagine that you take, we will do it for pentagons, but just because it's easier to speak, but it works for any n. So imagine you take a pentagon that has some area, and you look at the pentagon that has the smallest perimeter, or you take a pentagon with a given perimeter, and you look at the one that has the largest area. I claim the pentagon must be convex, because if it is not convex, it means there is some angle that is moving inside the shape. And if you have an angle that is moving inside the shape, then if you take this shape and you take this angle moving inside and you just reflect it across, you will have an angle moving outside. And if you replace an angle that is moving inside the shape by an angle moving outside the shape, you will not change the perimeter because you have just reflected something, but the area will have increased because when it is pointed inside, you will cover new area that was not covered by doing this. So if the polygon is to be the optimal polygon, if it is the polygon with the largest area, it must have been convex to start with, otherwise you can improve it. Okay, and now also the polygon must be, I say, equilateral. Okay, why equilateral? Equilateral means all of its sides have the same length. So imagine if it is not true. We do a proof by contradiction. Imagine you have a polygon that has 2 sides that are not the same. Okay, 2 sides are not the same. If 2 sides are not the same, it means you can find somewhere 2 sides that are consecutive and not the same. So you have a side here and then the next side, and they're not the same size. Now, this is in a big polygon, but you can consider the triangle that is obtained as follows. You take a line that joins the base of these sides, and you obtain a small triangle there. Okay? If you obtain a small triangle there, you can imagine that you take the corner and you can move it parallel to this side. If you move it parallel to this side, the area will not change in this small triangle because you use the formula base times height divided by 2. But when you move the side parallel to the base of the triangle, the perimeter will change. And I have said before, and I hope it was clear, that to obtain the shortest perimeter, you must choose the middle. You must place the corner so that the sides are equal. Okay, so if you start with the polygon, let me repeat this. You start with the polygon. You imagine that 2 consecutive sides are not the same. Then you can imagine that you have a line going to the base of this triangle formed by these two sides, and you can move the corner parallel to this side that is obtained by the base. And when you do this dynamic construction and you move the point, the area will not change at all. They're all of the same area, but by moving the point where the two sides have the same length, you will have the shortest possible perimeter. So if your initial polygon was optimal, you must have equal side length between these two. And this is the same everywhere. I was doing a proof by contradiction, so now I contradicted that the polygon was optimal because I can change the side length, move the point and get a better polygon. So if I imagine in my mind's eye, the best polygon, if it is not with equal angle, I can change it and it increases it diminishes the area without changing the perimeter. And so I have a contradiction because I get a better polygon and the initial polygon was not optimal. Similarly, it is possible to show that the polygon must have equal angle, but I will not discuss this. It is a similar geometric construction. Okay, so the strategy is imagine in your mind that the polygon that you have in front of you is the best. If it's not convex, you can improve it. If it's not equilateral, you can improve it. If it's not equiangular, you can improve it. And in each case, you get closer and closer to something that is a regular polygon. And so we have proved Zenodorus theorem. Now, Zenodorus theorem says something very nice, that for polygons, the best polygon is the most symmetric one. It is very similar to the isoperimetry problem where we want to obtain a circle, but it is only in the class of polygon, not in the class of all shapes. Now, imagine the following thing. If we take polygons that are regular, say like a square, pentagon, and so on, then the more sides there are, the nearest it looks like a circle. And now it is an exercise for you to solve. Imagine you take a regular polygon with n sides and they are of length c. Then the area of this polygon will be given by this formula. It is n times c squared divided by 4 tangent of pi over n. This will be the area. It is a trigonometric exercise if you want. And there are n sides of length c, so the perimeter is n times c. This is clear. And we said that the isoperimetric ratio is 4 pi times the area divided by pi squared. So if I write this in this case, I get pi divided by n over time pi over n. Okay, and this is the isoperimetric ratio. In this case, this is clearly smaller than 1. So, I mean, these figures all satisfy the isoperimetric inequality. I mean, it's just an observation. But also, Zenodorus proved that this isoperimetric ratio, it is increasing as the number of sides goes to infinity. Imagine that you take this here, this quantity, pi divided by n tangent of pi over n, and you take the limit as n goes to infinity. Then it is an exercise also for you, for a computation of limit, that when n goes to infinity in this formula, well, you have all of this that goes to 1. And you can see this already, because if you take tangent of pi over n, it is sine of pi over n divided by cos of pi over n. And you see that you will have sine of pi over n, and you have an n in front of it. So in some sense, you will have to use something like the limit of x times sine x tends to 1 when x goes to 0. And by doing this, you will see that you have increasing sequence that goes to the isoperimetric ratio for a disk, which is 1. Okay? And let me illustrate this with the computation. So I take this formula 4 pi a over pi squared, and I will just show you on some different shapes. So in the case of a triangle, I get this value. For a square, I get this value. And you see for pentagon, I get this. And when I increase the number of sides, you see it's getting nearer and nearer to 1, 0.96, 0.99. And now I have it looks on your screen like a circle, but it is a regular polygon with 72 sides, and it is 0.999 already. And I have done it one more time with 180 sides. And you see, I mean, it's just an illustration of the fact that this ratio converges to 1. So, I mean, we are very near a proof of the isoperimetric inequality. Because if you imagine that you have a polygon with a billion side, we know that the best polygon with the billion side would be the regular one. And we know that for the regular one, it is smaller than 1. So for any curve that is polygonal, we have proved the isoperimetric inequality. So historically, this is very important, and this is almost a proof. But it is not a proof, because there are some shapes that are not polygonal. You can make a curve that is not built of polygon, and then it is not proved yet. Okay. So historically, one very important way of proving this was discovered and developed by Euler in the 18th century. And the way that Euler did these things is by developing something called calculus of variations. And I will not go into details of calculus of variations here. Let me just say that this is a very important branch of mathematics for applied mathematics, engineering, and so on, because it allows for the connection between physical description of a problem and differential equations. So often you have physical problem that is described by, you want to minimize some energy, for instance, and by using calculus of variation, you can translate this into differential equations or partial differential equations. So these slides here I just described for historical purpose. It will be too quick maybe, but I just want to say there is this kind of mathematics that can be used to study these things. So imagine that you have a planar domain this time, but it is not polygonal. It is bounded by a smooth curve, like the one that is on the picture. So the area is the place, the part in blue, and it is bounded by some curve that has length 2 pi. I chose 2 pi for the constraint because it is like the perimeter of the unit disk, a circle of unit radius. Now I can imagine that I parameterize this curve by a function, like a parameterized curve, like I wrote here. And you have maybe seen in your calculus class something called the Green's formula or Green theorem, which allows to compute integral of quantities in a domain and bring them to an integral on the boundary. And this allows to write the area of this domain as an integral an integral of one variable given by this here. So the parameterization is given by x of t and y of t, and you can express the area like this. And the perimeter is also expressible as an integral, and this perimeter is given by the integral of this here. So I don't know if you can hear, there is a thunderstorm here right now. Okay, so when you have the area expressed by an integral and the perimeter expressed by an integral, then you are in business to do calculus of variations. And what you want to do is you look at the function, at the action, which is the area. For each curve, you look at this integral, and you have a constraint that is, you want this other integral to be equal to 2 pi. And I'm not going to do in details, but what Euler did is he showed that if you take a domain that has maximal value for the area, among those that have perimeter 2 pi, then the curve must satisfy this system of ordinary differential equation. So the curve is given by x, gamma of t is x of t, comma, y of t. And so the derivative of y with respect to t plus the double derivative of x is 0, and minus the derivative with respect to x of x plus the double derivative of y equal to 0. And this is maybe an exercise in differential equation to show that the general solution of this system is given by something like this. So constant plus cosinus of something and a constant plus sinus of something. And this is the parameterization of a circle. If you look at this, it is a circle centered at x0, y0 with radius 1, because cos and sin are a parameterization of a circle. So Euler considered this as a solution of the isoperimetric problem for more general. It's not polygonal this time, it's for a smooth curve. This is interesting. Now this solution is based on calculus of variation, and I just have a slide here. I did not even translate it from French because because I don't want to go into it. It's just an explanation of what calculus of variation is, but it takes several hours or weeks to understand it properly. But I just want to tell you that there is something called calculus of variation. It is very important. I hope you will study it someday or that you have studied it, but that's not my point. My point is now to move to a different character in my story. So calculus of variation is very nice, but it is based on calculus. And calculus in the 18th century was very new. And calculus and analysis was not something that many people liked. In the beginning, it was considered like maybe some kind of magic. And many mathematicians did not like anything that is done with it. And Jakob Steiner was one of them. So Jakob Steiner, he was a Swiss geometer, a mathematician who really did not like calculus. And in fact, it is a misnomer. He really hated calculus. For him, anything that could be deduced using calculus should be also deduced from purely geometric method. And he hated the calculus of variation and all of this development. So to show that one can do everything using a purely geometric method, he proposed a proof of the isoperimetric problem, a solution without using any of this derivative and integral that Euler did. And I want to show you what his proof is. But before I show you what his proof is, I want you to now stay extremely sharp and think about why it does not work. I'm telling you in advance that there is something very deep that is not working in this proof. I'm also telling you that Steiner himself did not see the mistake. So if you don't see the mistake, you are not stupid, you are in very good company. Not many mathematicians could see this mistake. And the main idea of Steiner is the following. I just describe it without going in details first. Imagine that you take among all shapes of a given area, you in your mind's eye, you imagine the shape that has the smallest perimeter. And now you imagine that this shape is not a circle. And if it is not a circle, we will find a way to deform the shape and increase the area without touching the perimeter, or decrease the perimeter without touching the area. And in that case, we have a contradiction because we suppose that the shape has the largest area. If you start with the largest area, you're not supposed to be able to deform it and get a bigger area. If you do that, the thing you started with in your mind is not the best shape. So it is a proof by contradiction. Okay, let's think of why this is the case. Let's look at Steiner's proof. So take a figure in your head that has the biggest area possible, and imagine it's not a circle. So I tell you, it's hard to imagine because it's not possible, but we don't know this for the sake of the proof. Okay, now imagine that this shape, you look at this shape and you take lines and you move the lines parallel to themselves until they cut the perimeter in equal length. It's possible because when you start to touch the shape, all the perimeter is on one side, and when you touch a little bit more the shape, you have a lot of perimeter on one side and just a little on the other side. And then you increase, and at some point you divide the perimeter in two equal parts. Okay? I'm claiming that if the shape is the best shape, when I do this with the perimeter equal on each side, I must also have equal area on each side. Okay, why? Because if perimeter is equal on each side, but one of the sides has a bigger area, I will erase the figure on the side that has smaller area and replace it by a reflection of the side that had larger area. Okay, I repeat, I take a shape that has the same perimeter on each side of a straight line. If one of the sides of the straight line have a larger area, I keep it and I erase the figure on the other side and replace it by a mirror image on the other side. By doing this, I have exactly the same perimeter as in the original figure because I have chosen exactly where the perimeter is cut in two. But my total area will have increased because I have reflected the part with larger area. Okay, so it means if the shape is the best shape with the largest area. Naturally, in each direction, when I move a line and I cut the perimeter in two, I will have the same area as well. Otherwise, I would contradict that the figure I have in my head is the best figure. Now, also, imagine that you take just half this figure. You have this line, you have a line, and you have half the figure. So it's a shape there. And I claim that what we want to show is that this half figure is a half circle. Now, how in geometry can we characterize half circle? If you have a line like this and you have a half circle, the half circle is exactly the set of points for which, when you take a triangle, it will be a right angle triangle. So let me try to draw something on my sheet. I hope you will be able to see this. I draw a half circle and I draw a triangle inside it. So I hope everybody can see this. I have drawn a half circle like this, and if I take any point on it, if I do a triangle like this, the angle here is a right angle. Okay, and for each point on the half circle, I will have right angle. So in order this is a characterization of the half circle. If I take points that are not on the half circle, if they are outside, the angle here will be smaller, and if they are inside, the angle will be bigger. So in order to prove that this is a half circle, I must prove that for every point on the perimeter, on the boundary of the figure, I have a right angle. Okay, now by contradiction, I imagine this is not the case. If this is not the case, it means there is a point on the boundary of the figure. Maybe I will draw something else. Imagine that my figure is like this instead. So imagine instead this is half my figure. Maybe this time it's not a circle. I have this, and I would have the other half a reflection of this. And you see some points here are not. It's not a circle. So there are some points where when I take them, maybe here. When I take a point here, the triangle that is here, the angle here is not a right angle. Okay, but if I do this, now I will be able to move things around and obtain a same perimeter figure with a larger area. How would I do this? Well, I would cut the figure here and slide things open. I would keep this part and this part that I drew fixed and slide things open so that the angle in the middle here, I would slide the base here to make this angle in the middle a right angle. And one can prove that among all triangles here that have the same, like this side length is fixed, this side length is fixed, when I move it around, the one that has the largest area inside is the one with the right angle. So I must have right angle everywhere. And therefore, if I must have right angle everywhere, it must be a circle because this is a characterization of the half circle. Okay, I think this is maybe not completely clear what I'm saying, but the point here, I will send you all the GeoGebra files after if you want to share them with everyone, Raki. I'm sorry I could not switch screen, but I don't want to reboot my computer now. It would be a catastrophe. So the point of the proof, okay, the mistake is not in the details. The mistake is already in the strategy, okay? I'm saying, imagine, okay, I want just to discuss the strategy. The strategy is the following. We want to prove that if we look at all figures with the same perimeter, then the figure with the largest area is the disk. Now the proof that I showed you is as follows. Think of a figure that is not a disk and that has the largest, take in your mind's eye the figure that has the largest area among all of them with the same perimeter. Then imagine it is not a disk. Then we have just shown a way to transform this figure and it will have a larger area. So this contradicts the fact that the figure you have in your mind's eye was with the largest area. Okay, because if it was the largest area, you could not find another figure that has a larger area. My claim is that this argument is wrong already. But it is wrong for a specific and very subtle reason. Okay, and how am I going to convince you that this is wrong? I will prove something with the same strategy, something that you all will agree is wrong. Okay? And so I repeat, the strategy is to take in your mind's eye the figure with the largest area. If it is not a disk or a circle, I can move it around and it will have a larger area without changing the perimeter. Okay, in that sentence, there is a mistake. I will prove something with the same strategy that you will know is wrong. And this something is that 1 is the largest integer number. Okay, of course, it's not true that 1 is the largest integer number. But in 1913, a mathematician called Perron wanted to convince Steiner that his proof was wrong, and so he published the following proof as a kind of to annoy Steiner. So the first step will be where the mistake is, and then we will see it clearly. I will prove that 1 is the largest integer. First step, take in your mind's eye the largest integer. Okay, imagine the largest integer in your mind. If the largest integer is not 1, then we can find a way to find a new integer that is larger. Just replace n by n squared. Because if you take, for instance, 2, 3, etc., if you replace it by n squared, it will get bigger. So if you start with the largest integer, and you say, oh, if it is not equal to 1, I can make it bigger. So there is a contradiction because I suppose that the integer I started with was the largest integer. Thus, it's not possible, and so 1 is the largest integer. I'm sure you agree this is false because 1 is not the largest integer. And the mistake is clear. In the first sentence, when I say let n be the largest integer, well, there is no largest integer. You can always find a larger integer. There is no number that is bigger than all other number. Okay? So the problem is I assume that there exists something. And in all of the proofs that I have shown you of the isoperimetric stuff before, I have always asked you as a first step to say, take the figure in your head that has the largest area among all figures with a given perimeter. The problem is, how do we know that there exists a figure with the largest area? We don't even know that to begin with. Okay? Well, what does it mean if it does not exist? It means there could be like a sequence of figures, figure 1, 2, figure, and they will all have bigger and bigger and bigger and bigger area, all with the same perimeter, but they will not become something meaningful. Okay, maybe some of you are shocked because it is very counterintuitive. And the reason it is counterintuitive is that the answer is that there exists something. It exists. It is true that it is the circle, and we know it is the circle. But we cannot assume that it exists when we try to prove that it is the circle. So it's an existential crisis, and it is very important in the history of mathematics, these type of crises, because it shows that not only it's important to compute something, but if we don't know that the thing exists, we don't know what we're talking about. We don't know if we're computing something that makes sense. So the mistake is everywhere. Even in the beginning for polygon, I have supposed that there exists a polygon with the best solution. I have supposed that there is a n-gon that is the best, and then I have shown it is the regular polygon. So now I have something that I like to call the ontological isoperimetric problem. If I look at all the figures in the plane that have the same perimeter, does there exist a figure with the area that is the largest? And if you know that there exists one, then you can prove it is a disk. And I called, now if you look at the proof of Steiner's theorem, it is a proof of the following statement, and it is a proof without mistake of the following statement. If there is a plane figure for which the area is the largest, then it is a circle. Okay? The mistake is everywhere, even in the proof by calculus of variation. The way to go from a maximization problem for some physical quantity to a differential equation, it assumes that there is a solution. Okay, so everywhere there is this problem. And actually, I wanted to show you how people, I will maybe skip this, I don't want to take you too long, but a modern proof that there is that there exists a maximizer could go like this. I don't know the level of mathematics, I don't know if you know metric spaces and such things. But if we look at all the bounded convex sets in the plane, we can build some metric space out of this using something called the Hausdorff distance. And if we look on this metric space that is made of shapes, you can look at the two functions. One of them gives the area of the domain, and the other one the length of its boundary. And if you do things properly, these functions are continuous, and the set that you are working with is compact. And there is something that is well known that you know from analysis or calculus. If you have a compact set with a continuous function, the maximum is reached at some point. And you can set up this whole problem so that looking for the existence of a shape that maximizes the area is looking for a maximum of a continuous function on a compact space. And it exists because of that. Okay, I go quickly here just to say my point here is that doing rigorous modern mathematics has some very useful point. It's not just cloud shoveling, like I call it. Now, to conclude, I will not do everything else I have. What I have spoken about is an isoperimetric type problem. It's a problem that links the area with the perimeter. And in mathematics, there are very nice inequalities that links other quantities, not just area and perimeters. Let me show you a few. So in the case of the bubble, it is not area and perimeter, it is volume and area of the boundary. And we know also that there is an isoperimetric inequality for this. The difficulty in this case is much bigger because you can have surfaces that have, see these surfaces that I have pictured here, they all have the same area, despite having very complicated shapes. It is more difficult because we live in a three-dimensional world. If we are in two-dimensional world, we cannot grow some things like this without changing the length of the boundary very much. In this case, it's possible, and it makes the problem much harder to study. But it was done, and it is something that is modern mathematics from 20th century. You can also study the shapes of bubbles, not just one bubble, but what happens when two bubbles are touching each other. And it is now proved since 2002 that we know exactly what the shape is. I don't want to do this, but this is called the double bubble conjecture, and it was proved in 2002. Now, in my own research work, I study vibration problems. So I look at a drum head, like a regular drum or even an Indian tabla. And you can ask you look at the resonances, the frequencies of this, and they form sequence of frequencies, and you can ask what shape to give so that the frequency is the smallest or the largest. And this gives theorems about shapes. Here you have some optimal shapes for eigenfrequencies. They are not known theoretically, but there is numerical simulations in this case. This is just an overview of different things. And I want to conclude with this last slide where I present something, I would say, cute, but meaningful scientifically. One of the things that you could ask is in physics or in engineering, if you have a homogeneous material and you heat it at a certain temperature and you want the heat loss to be minimized. So what shape should you give it? Well, you should not give it imagine you take a metal and you make a thin sheet with it, then it will cool very quickly. And it turns out that the best shape is to make a ball with it. And Polya, a famous mathematician from 20th century, described this by saying that the reason that cat sleeps like this, at least in cold countries, is because they want to minimize their heat loss. And this is also an isoperimetric type problem. There is a way to formulate this by saying you fix the volume of something. Okay, definitely a cat is not homogeneous, but it is just an analogy. You fix the volume and you ask what shape should you give that volume so that the heat loss, which is possible to define mathematically, is minimized, and the answer is that it is a ball. Okay, I hope, despite not being able to share the screen like I wanted and everything else, I hope it was possible to follow this talk. I'm very, very happy that you gave me the opportunity to speak here. Thank you very much for your attention.
Any questions? Any questions?
You can
unmute and ask question.
So I see there were more than 100 people participating. This is one of my largest attendance in my life. Thank you for coming.
Any questions? Okay.
I see people are commenting in the chat also, but
I think no questions.
no problem. Thank you very much. I will go back to sleep.
Yes. Thank you, sir, for your lovely talk, and thank you for your time. And
It is my pleasure.
Early. Okay. I thank head of the department, Dr. P.R. Humphrey, and principal Dr. G.K. Kittur, sir, and KLS management for giving an opportunity to organize a webinar. And thank you, Dr. Alexandra Juzon, for taking your precious time for us.
Thank you. I appreciate very much. Also give my most sincere thanks to Head of Department RaGa Hampioli and to the principals of KLS Cocktail Institute, Diane Kittur. Thank you very much.
Thank you, sir. Our feedback link is shared in chat box. Please check.
Bye-bye.
Okay. Bye.
ഇതുള്ളതിനെ ഒന്നും തിരിയാ